Imagine a world where machines can think, learn, and even outsmart humans. This is no longer science fiction, but the reality of artificial intelligence, or AI. From self-driving cars to virtual assistants, AI is rapidly transforming our lives. But the journey of AI is not a recent phenomenon. It is a captivating tale that spans centuries, filled with brilliant minds and groundbreaking discoveries. This essay embarks on a thrilling exploration of AI through the ages. We will journey from the ancient myths that first imagined intelligent machines to the modern marvels of deep learning. Fasten your seatbelts as we delve into the fascinating history of AI. Our adventure begins in ancient Greece, where myths whispered of automatons and philosophers pondered the nature of thought. We then fast forward to the 19th century, where pioneers like Charles Babbage and Ada Lovelace laid the groundwork for computational thinking. The mid-20th century marks the birth of AI as we know it. Alan Turing, a visionary mathematician, proposed the idea of machines that could mimic human intelligence. The Dartmouth Conference in 1956 formally established AI as a distinct field of study. From the early triumphs and challenges to the rise of machine learning and the transformative power of deep learning, we will witness the evolution of AI. This journey will culminate in the present day, where AI is deeply intertwined with our lives, and we will ponder the profound implications for the future. Long before the digital age, the seeds of AI were sown in the fertile ground of human imagination. Ancient myths, those timeless tales passed down through generations, offer a glimpse into humanity's early fascination with artificial beings. The ancient Greeks, renowned for their philosophical and technological prowess, wove stories of automatons, mythical beings crafted from metal and imbued with intelligence. One such tale speaks of Talos, a giant bronze automaton tasked with guarding the island of Crete. Forged by the god Hephaestus, Talos possessed superhuman strength and tireless vigilance, patrolling the island's shores and hurling boulders at intruders. This mythical being embodies the early human desire to create artificial guardians, protectors capable of surpassing human limitations. Beyond the realm of myth, ancient philosophers grappled with the nature of intelligence itself. Aristotle, the renowned Greek philosopher, explored the concept of reasoning and logic, laying the groundwork for future inquiries into the potential for mechanical thought. His work, along with the musings of other great thinkers, planted the seeds for the idea that intelligence could be understood and perhaps even replicated through artificial means. These early imaginings, though rooted in fantasy, reflect a fundamental human aspiration to create beings in our own image, capable of independent thought and action. While the realization of such aspirations lay centuries in the future, these early myths and philosophical inquiries laid the groundwork for the eventual emergence of artificial intelligence as a field of scientific endeavor. As centuries passed, what was once confined to the realm of myth began to take on a more tangible form. The invention of clockwork mechanisms in the Middle Ages marked a significant step towards realizing the dream of artificial beings. These intricate devices, driven by gears and springs, demonstrated the potential for creating machines that could mimic certain aspects of human behavior. The intricate clockwork automatons of the 18th century, often crafted in the image of humans or animals, captured the imagination of the era. These mechanical marvels, capable of performing complex movements and even playing music, blurred the lines between artifice and life, further fueling the desire to create truly intelligent machines. The allure of these automatons extended beyond mere entertainment. They sparked philosophical debates about the nature of life itself. Could a machine, no matter how complex, truly be considered alive? Or was there an essential spark, a vital force that separated the living from the inanimate? These questions, echoing the musings of ancient philosophers, laid bare the profound philosophical implications of attempting to create artificial intelligence. The clockwork creations of this era, though lacking the sophistication of modern AI, represent a crucial step in the journey towards creating thinking machines. They demonstrated the power of human ingenuity to design and build complex mechanisms, setting the stage for the groundbreaking advancements that would follow. Section 3. From Myth to Mechanism. The transition from mythical automatons to the tangible gears and levers of clockwork creations marked a significant shift in the perception of artificial intelligence. No longer solely the realm of fantastical tales, the pursuit of creating intelligent machines began to take shape in workshops and laboratories, driven by a growing understanding of mechanics and a desire to push the boundaries of human ingenuity. This shift from myth to mechanism coincided with a broader cultural embrace of scientific inquiry. The Enlightenment, with its emphasis on reason and empirical observation, fostered an environment ripe for exploring the potential of artificial intelligence. Thinkers and inventors began to envision machines not just as tools for labor, but as potential partners in intellectual pursuits, capable of augmenting human capabilities. The development of increasingly sophisticated calculating machines further fueled this ambition. Devices like the Pascaline and the stepped reckoner, though rudimentary by modern standards, demonstrated the potential for machines to perform complex mathematical operations, tasks traditionally reserved for the human mind. This growing computational power hinted at the possibility of machines one day surpassing human capabilities in certain domains. As the 19th century dawned, the stage was set for a new era of innovation, one that would see the birth of the first programmable computers and lay the foundation for the field of artificial intelligence as we know it today. The journey from mythical beings to mechanical marvels was nearing its next act, one that would see the fusion of mathematics, engineering, and the audacious dream of creating machines capable of thought. Section 1. The Analytical Visionary. In the heart of the 19th century, amidst the whirring gears of the Industrial Revolution, a visionary mind emerged, forever altering the trajectory of artificial intelligence. Charles Babbage, an English mathematician and inventor, dared to dream of a machine that could transcend the limitations of simple calculation and delve into the realm of true computation. His creation, the analytical engine, stands as a testament to his ambition and a precursor to the modern computer. Babbage's analytical engine was unlike any machine the world had ever seen. Conceived as a general-purpose computer, it was designed to perform a wide range of calculations, not merely a fixed set of operations. This revolutionary concept, driven by Babbage's conviction that machines could extend the reach of human intellect, laid the groundwork for the development of the programmable computers that would shape the 20th century. At the heart of the analytical engine lay a sophisticated system of gears, levers, and punched cards, all working in concert to process information. Input data, instructions, and even programs were to be fed into the machine using punched cards, a concept inspired by the Jacquard loom, which used similar cards to control the weaving of complex textile patterns. This ingenious system allowed for a level of programmability and flexibility previously unimaginable in mechanical devices. Although the analytical engine was never completed in Babbage's lifetime, hampered by the limitations of 19th century engineering and funding, its impact on the future of computing cannot be overstated. Babbage's vision, meticulously documented in his drawings and writings, served as a beacon for future generations of inventors and computer scientists, inspiring them to push the boundaries of what machines could achieve. Section 2. The Enchantress of Numbers. While Charles Babbage provided the mechanical ingenuity behind the analytical engine, it was Ada Lovelace, a brilliant mathematician and the daughter of Lord Byron, who breathed life into its potential. Recognizing the machine's revolutionary capacity for more than just numerical calculation, Lovelace envisioned a future where computers could transcend mere arithmetic and manipulate symbols, essentially processing any information that could be expressed in a systematic way. In her annotations of Babbage's work, Lovelace penned what is widely considered to be the first computer program. This algorithm, designed to be processed by the analytical engine, went beyond simple calculations and demonstrated the machine's ability to manipulate numbers in a sequence to produce a desired result. This groundbreaking work earned Lovelace the title of the first computer programmer, a testament to her visionary understanding of the machine's potential. Lovelace's insights into the analytical engine extended beyond its computational power. She grasped the profound implications of a machine that could manipulate symbols, recognizing that such a device could potentially process music, text, and even abstract concepts. This visionary understanding, far ahead of its time, laid the groundwork for the development of computers as we know them today, machines capable of handling a vast array of information beyond simple numbers. Despite living in an era where women in science were often marginalized, Lovelace's contributions to the field of computing were significant and enduring. Her work, often overshadowed by Babbage's mechanical achievements, helped to shape the future of technology, paving the way for the digital revolution and the birth of artificial intelligence. Section 3. Bridging the Divide. The combined efforts of Babbage and Lovelace, the mechanical genius and the visionary programmer, represent a pivotal moment in the history of artificial intelligence. Their work, though seemingly confined to the realm of theoretical machines and intricate algorithms, transcended the limitations of their time and laid the foundation for the development of modern computers. The analytical engine, though never fully realized, served as a tangible manifestation of the growing belief that machines could be more than just tools for calculation. They could be partners in exploration, capable of augmenting human intellect and pushing the boundaries of knowledge. The legacy of Babbage and Lovelace extends beyond the realm of engineering and mathematics. Their collaboration, a testament to the power of shared vision and intellectual curiosity, highlighted the importance of interdisciplinary thinking in advancing scientific endeavors. Just as the analytical engine combined mechanical precision with computational concepts, future breakthroughs in artificial intelligence would require the combined efforts of mathematicians, engineers, philosophers, and visionaries from diverse fields. The impact of their work resonated throughout the 19th and 20th centuries, inspiring generations of scientists and engineers to pursue the dream of creating intelligent machines. The development of the first electronic computers in the mid-20th century, machines that finally fulfilled the promise of Babbage's vision, can be traced back to the fundamental principles first explored in the design of the analytical engine. As we stand on the cusp of a new era of artificial intelligence, with machines capable of learning, adapting, and even surpassing human capabilities in certain domains, it is essential to remember the foundational work of those who came before. Section 1. The Imitation Game. As the world emerged from the shadow of World War II, a new era of technological innovation dawned, one that would see the birth of the electronic computer and the formalization of artificial intelligence as a distinct field of study. At the forefront of this revolution stood Alan Turing, a British mathematician and codebreaker whose groundbreaking work during the war had proven instrumental in deciphering the Enigma machine, a feat that helped to turn the tide of the conflict. Turing's wartime experiences, though shrouded in secrecy at the time, had exposed him to the immense potential of computing machines. His work on the Enigma code had convinced him that machines could be far more than just glorified calculators. They could be tools for manipulating symbols, for processing information and making decisions in a way that mirrored and perhaps even surpassed human capabilities. In 1950, Turing published a seminal paper titled Computing Machinery and Intelligence, in which he posed a deceptively simple question: can machines think? This question, seemingly straightforward, struck at the heart of what it meant to be intelligent, challenging, long-held assumptions about the unique nature of human thought. To address this question, Turing proposed a thought experiment that would become known as the Turing test. The Turing test, as conceived by Turing, involved a human evaluator engaging in a conversation with both a human and a machine without knowing which was which. If the evaluator could not reliably distinguish between the human and the machine based solely on their responses, then, Turing argued, the machine could be considered to exhibit intelligent behavior. This test, though controversial and subject to ongoing debate, became a cornerstone of artificial intelligence, providing a benchmark for measuring machine intelligence and sparking countless discussions about the nature of consciousness and the potential of artificial minds. Section 2. A new field emerges. The year 1956 marked a pivotal moment in the history of artificial intelligence, a year that saw the convergence of brilliant minds and the formal recognition of AI as a distinct field of study. In the summer of that year, a group of visionary researchers gathered at Dartmouth College for a workshop that would come to be known as the Dartmouth Conference, an event widely considered to be the birthplace of artificial intelligence as we know it today. The Dartmouth Conference, organized by John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon, brought together some of the most prominent figures in the nascent field of computing, including pioneers in mathematics, engineering, and cognitive science. The goal of the conference, as outlined in their ambitious proposal, was to explore the possibility of creating thinking machines, machines capable of simulating human intelligence in all its forms. Over the course of the summer, the attendees of the Dartmouth Conference engaged in lively discussions, debates, and collaborative brainstorming sessions, laying the groundwork for the future of artificial intelligence. They explored a wide range of topics, from symbolic reasoning and problem solving to the potential for machines to learn from experience and adapt to new information. It was at this conference that the term artificial intelligence was coined, a term that would come to encompass a vast and rapidly evolving field of research. The Dartmouth Conference, though lacking the concrete breakthroughs of some later AI milestones, served as a catalyst for progress in the field. It fostered a sense of community among AI researchers, providing a platform for sharing ideas, forming collaborations, and establishing a common set of goals. The spirit of optimism and intellectual daring that permeated the conference would inspire generations of AI researchers, propelling the field forward through periods of both rapid advancement and frustrating setbacks. Section 3. The dawn of the AI age. The years following the Dartmouth Conference witnessed an explosion of interest in artificial intelligence as researchers around the world, inspired by the promise of creating truly intelligent machines, embarked on ambitious projects to turn theory into reality. Early AI research focused primarily on symbolic AI, a paradigm based on the idea that intelligence could be represented through the manipulation of symbols such as words, numbers, and logical relationships. One of the earliest and most influential AI programs was the Logic Theorist, developed by Alan Newell, J.C. Shaw, and Herbert Simon in 1955. The Logic Theorist was designed to prove mathematical theorems, a task that had long been considered the exclusive domain of human mathematicians. The program's success in proving a significant portion of the theorems in Russell and Whitehead's Principia Mathematica sent shockwaves through the scientific community, demonstrating the potential of AI to tackle complex intellectual tasks. Another groundbreaking program of this era was the General Problem Solver, or GPS, also developed by Newell, Shaw, and Simon. As its name suggests, the GPS was designed to be a more general-purpose problem-solving program, capable of tackling a wider range of problems than its predecessor. The GPS employed a technique known as means-ends analysis, in which the program would break down a problem into smaller subproblems, solve those subproblems, and then combine the solutions to arrive at a solution for the original problem. While the GPS was ultimately limited in its ability to solve truly complex real-world problems, it represented a significant step forward in the development of general-purpose AI systems. These early successes, though impressive for their time, were but a glimpse of the potential that lay ahead. The field of artificial intelligence was still in its infancy, and many challenges lay ahead. Challenges that would test the limits of both human ingenuity and the rapidly evolving capabilities of computing machines. Yet the seeds of a technological revolution had been sown, and the quest to create truly intelligent machines was well underway. Triumphs and tribulations. The early years of AI research were marked by excitement and optimism. Each new program seemed to bring the dream of intelligent machines closer. However, beneath the surface, cracks began to appear. Researchers encountered unforeseen challenges and limitations. Section 2. The limits of logic. Early AI research, with its emphasis on symbolic AI, had achieved remarkable success in domains characterized by clear rules and logical relationships, such as mathematics and game playing. However, these early systems struggled to replicate the more nuanced aspects of human intelligence, such as understanding natural language, recognizing objects in images, and navigating the complexities of the real world. The limitations of symbolic AI stemmed in part from the difficulty of representing complex real-world knowledge in a format that could be processed by computers. Human knowledge, unlike the neatly defined rules of a game or the axioms of a mathematical system, is often imprecise, context-dependent, and acquired through a lifetime of experiences. Capturing this richness and subtlety in a set of rules or symbols proved to be a formidable challenge. Moreover, symbolic AI systems relied heavily on explicit programming, with every step of the reasoning process needing to be carefully coded by human engineers. This approach, while effective for well-defined problems, proved to be brittle and inflexible when faced with the unpredictable nature of the real world. As AI systems were tasked with handling more complex and dynamic environments, the limitations of this rule-based approach became increasingly apparent. The realization that symbolic AI alone might not be sufficient to achieve artificial general intelligence, the kind of intelligence that could truly rival human capabilities, led to a period of soul-searching within the AI community. Researchers began to explore alternative approaches, seeking inspiration from fields such as neuroscience and cognitive psychology in the hopes of developing more robust and adaptable AI systems. Section 3. A winter's chill. By the mid-1970s, the initial wave of enthusiasm for artificial intelligence had given way to a more sobering reality. The early successes, though significant, had not translated into the kind of transformative breakthroughs that many had envisioned. The limitations of symbolic AI, coupled with the immense difficulty of replicating the full spectrum of human intelligence, led to a period of disillusionment and reduced funding, a time that would become known as the AI winter. The AI winter was a time of introspection and reassessment for the field. Funding for AI research dwindled, and many researchers shifted their focus to other areas of computer science that seemed to offer more immediate practical applications. The term artificial intelligence itself became somewhat taboo in academic circles, often associated with overhyped promises and unrealistic expectations. However, despite the challenges and setbacks, the pursuit of artificial intelligence did not disappear entirely. Small pockets of researchers, driven by a deep-seated belief in the potential of AI, continued to explore new ideas and approaches, laying the groundwork for a future resurgence. These researchers, often working with limited resources and facing skepticism from their peers, focused on developing more robust learning algorithms, inspired by biological systems and the workings of the human brain. The AI winter, though a difficult period for the field, served as a necessary corrective to the exuberance of the early years. It forced researchers to confront the limitations of existing approaches, to refine their understanding of the complexities of intelligence, and to develop new methods that would pave the way for the remarkable progress that lay ahead. Section 1. Machines that learn. As the chill of the AI winter began to thaw, a new paradigm emerged, one that would fundamentally reshape the landscape of artificial intelligence. This new approach, known as machine learning, shifted the focus from explicitly programming computers to perform specific tasks, to designing algorithms that allowed computers to learn from data, to identify patterns, and to improve their performance over time. Machine learning, in its essence, is about empowering computers to learn from experience, to adapt to new information, and to make predictions or decisions without being explicitly programmed for every possible scenario. Instead of relying on handcrafted rules, machine learning algorithms are trained on vast data sets, allowing them to discover hidden patterns and relationships that would be impossible for humans to discern. This paradigm shift was driven in part by the growing availability of data, the lifeblood of machine learning. As computers became more powerful and storage capacity increased exponentially, researchers gained access to unprecedented amounts of data, from text and images to sensor readings and financial transactions. This data deluge, once a logistical challenge, became a goldmine for machine learning, providing the raw material for training increasingly sophisticated algorithms. The rise of machine learning marked a fundamental departure from the rule-based approach of symbolic AI. Instead of attempting to codify all human knowledge into a set of rules, machine learning embraced the power of data-driven discovery, allowing computers to learn and adapt in ways that mirrored, at least in some respects, the remarkable flexibility of the human mind. Section 2. The rise of neural networks. Among the many machine learning techniques that emerged during this period, one stood out for its ability to capture the complexity of human-like learning artificial neural networks. Inspired by the structure and function of the human brain, neural networks are composed of interconnected nodes or neurons, organized in layers, each layer processing information and passing it on to the next. The power of neural networks lies in their ability to learn complex patterns and relationships from data through a process known as training. During training, a neural network is presented with a set of input data and corresponding desired outputs. The network then adjusts the strength of the connections between its neurons, iteratively refining its internal model to minimize the difference between its predicted outputs and the actual outputs. Early neural networks, while promising, were limited in their capacity and prone to getting stuck in local optima, failing to find the best possible solution. However, advances in computing power, coupled with the development of new training algorithms, such as backpropagation, led to a resurgence of interest in neural networks in the 1980s. Neural networks proved particularly adept at tasks such as image recognition, natural language processing, and pattern detection, areas where traditional rule-based approaches had struggled. Their ability to learn from raw data without the need for explicit feature engineering made them well-suited for tackling complex, real-world problems where the underlying rules were difficult or impossible to define. Section 3. A new era of intelligence. The resurgence of neural networks, coupled with the growing availability of data and advances in computing power, ushered in a new era of artificial intelligence, one marked by remarkable progress and a renewed sense of optimism. AI systems, powered by machine learning and fueled by data, began to surpass human capabilities in specific domains, demonstrating their prowess in tasks ranging from game playing to medical diagnosis. One of the most notable milestones of this era was the victory of IBM's Deep Blue computer over chess grandmaster Garry Kasparov in 1997. Deep Blue, a specialized chess-playing machine that combined brute force computation with sophisticated evaluation functions, demonstrated the ability of AI systems to outperform even the most skilled human players in games of strategy and complex calculation. The victory of Deep Blue, while significant, was soon eclipsed by even more impressive feats. In 2011, IBM's Watson supercomputer, equipped with advanced natural language processing capabilities, triumphed over human champions on the game show Jeopardy, showcasing the ability of AI systems to understand and respond to complex questions posed in natural language. These successes, though limited to specific domains, highlighted the potential of AI to augment and even surpass human capabilities in a wide range of tasks. The stage was set for a new wave of AI innovation, one that would see AI systems move beyond the laboratory and into the real world, transforming industries, disrupting traditional business models, and raising profound questions about the future of work, society, and the very nature of intelligence itself. Section 1. The Deep Learning Revolution. The early 21st century witnessed a seismic shift in the field of artificial intelligence with the advent of deep learning. Building upon the foundation of neural networks, deep learning introduced a new level of sophistication, enabling machines to learn from vast amounts of data with unprecedented accuracy and efficiency. This breakthrough marked a turning point, propelling AI from the realm of specialized applications into a transformative force across various industries. Deep learning distinguishes itself from traditional neural networks through its sheer scale and complexity. While early neural networks were limited to a handful of layers, deep learning models boast hundreds or even thousands of layers, allowing them to discern intricate patterns and representations in data. This depth of analysis, coupled with the explosion of available data and advancements in computing power, unleashed the true potential of neural networks, enabling them to tackle tasks previously considered the exclusive domain of human perception and cognition. The impact of deep learning reverberated throughout the field of AI, revolutionizing areas such as image recognition, natural language processing, and speech synthesis. Tasks that had long stymied traditional AI systems, such as accurately identifying objects in images or translating languages with human-like fluency, became achievable with remarkable accuracy. This newfound capability opened up a world of possibilities, paving the way for applications ranging from self-driving cars to personalized medicine. The deep learning revolution marked a profound shift in the capabilities of AI, demonstrating its potential to not only mimic, but also surpass human performance in specific domains. This breakthrough ignited a wave of investment and innovation, drawing researchers and entrepreneurs alike to explore the vast potential of deep learning to solve real-world problems and reshape entire industries. Once confined to research labs and science fiction novels, artificial intelligence has rapidly infiltrated nearly every aspect of modern life. From the moment we wake up to the time we go to bed, AI-powered devices and services surround us, often seamlessly integrated into our daily routines that we hardly notice their presence. One of the most ubiquitous examples of AI's pervasiveness is the smartphone, a device that has become an indispensable part of modern life. Within these sleek gadgets reside a multitude of AI-powered features, from voice assistants like Siri and Alexa that respond to our queries to facial recognition software that unlocks our phones with a glance. Beyond our personal devices, AI has made significant inroads into various industries, transforming the way we work, shop, and interact with the world around us. In healthcare, AI is being used to analyze medical images, diagnose diseases with greater accuracy, and even personalize treatment plans. In finance, AI algorithms power fraud detection systems, provide personalized investment advice, and automate trading decisions. The transportation sector is also undergoing a radical transformation thanks to AI. Self-driving cars, once a futuristic fantasy, are rapidly becoming a reality, promising to revolutionize transportation systems and reduce accidents. AI-powered traffic management systems are already optimizing traffic flow in cities, reducing congestion, and improving efficiency. As AI continues to evolve at an unprecedented pace, its integration into our daily lives will only deepen. From personalized recommendations on streaming services to AI-powered tutors that cater to individual learning styles, AI has the potential to enhance our lives in countless ways. However, this rapid proliferation of AI also raises important ethical and societal questions that we must address as we navigate this new technological landscape. The rapid advancements in artificial intelligence, particularly in deep learning, have ushered in an era of ubiquitous intelligence, where AI is no longer a separate entity, but rather an invisible force permeating every aspect of our world. This pervasive intelligence is transforming industries, reshaping societies, and challenging our very understanding of what it means to be human in the digital age. The proliferation of sensors, interconnected devices, and the Internet of Things, IoT, has created an unprecedented amount of data, providing fertile ground for AI algorithms to thrive. This data, combined with the power of cloud computing, allows AI systems to learn and adapt at an unprecedented scale, constantly improving their performance and expanding their capabilities. One of the most profound implications of ubiquitous intelligence is the automation of tasks previously thought to require human cognition. From driving cars to providing customer service, AI systems are increasingly taking over roles once performed by humans, raising questions about the future of work and the potential displacement of certain job categories. However, the rise of ubiquitous intelligence also presents enormous opportunities. By automating routine tasks, AI has the potential to free up human workers to focus on more creative, strategic, and fulfilling endeavors. In healthcare, AI can assist doctors in making more accurate diagnoses and developing personalized treatment plans, leading to better patient outcomes. As AI becomes increasingly integrated into the fabric of our lives, it is crucial that we approach its development and deployment with careful consideration. Ethical considerations, such as bias in algorithms, data privacy, and the potential misuse of AI, must be addressed to ensure that this powerful technology is used for the betterment of humanity. As we stand at the cusp of a new era defined by artificial intelligence, the road ahead is paved with both unprecedented opportunities and complex challenges. The exponential growth of AI, fueled by deep learning and ubiquitous data, has set in motion a technological revolution that promises to reshape our world in profound ways, touching upon every facet of human endeavor. The potential benefits of AI are undeniable. In healthcare, AI has the potential to accelerate medical breakthroughs, enabling personalized treatments, early disease detection, and more effective drug discovery. In manufacturing, AI-powered robots can work alongside human counterparts, enhancing productivity, improving safety, and enabling the creation of entirely new products and processes. However, this technological leap forward is not without its potential pitfalls. The increasing automation of jobs, driven by AI and robotics, raises concerns about workforce displacement and the need for new models of education and job training to prepare individuals for the jobs of the future. The ethical implications of AI, including algorithmic bias, data privacy, and the potential misuse of AI for malicious purposes, demand careful consideration and proactive measures to mitigate potential harm. The development and deployment of AI must be guided by a human-centered approach, one that prioritizes human well-being, fairness, and accountability. As we venture further into the age of intelligent machines, it is imperative that we proceed with caution, ensuring that AI serves as a tool for progress, empowering humanity to reach its full potential while mitigating the risks associated with this powerful technology. The future of artificial intelligence is not a predetermined outcome, but rather a tapestry woven from the choices we make today. It is a future that will be shaped by the collective efforts of researchers, policymakers, industry leaders, and citizens, all working together to harness the transformative power of AI while addressing its inherent challenges. International cooperation will be essential in navigating the complex landscape of AI governance. Establishing shared ethical principles, safety standards, and regulatory frameworks will be crucial to ensure the responsible development and use of AI on a global scale. Open dialogue and collaboration between nations will be essential to address the potential risks of AI while fostering innovation and ensuring that the benefits of this technology are shared widely. Education and public awareness will play a vital role in shaping a future where humans and AI can coexist and thrive. Fostering digital literacy, critical thinking skills, and an understanding of the potential benefits and risks of AI will empower individuals to navigate this rapidly evolving technological landscape. Investing in education and training programs will be essential to equip the workforce with the skills needed to succeed in an AI-driven economy. The journey into the age of artificial intelligence is not one that we undertake alone. It is a journey that will require collaboration, creativity, and a steadfast commitment to ethical principles. By embracing a human-centered approach, fostering dialogue, and working together to address the challenges and opportunities that lie ahead, we can shape a future where AI empowers humanity to create a more just, equitable, and prosperous world for all.